Hello everybody, welcome to my devlog. In this video I will be covering resistance, changes made to incorporate resistance, and changes I made to the elemental resistance system. This one should probably be a little bit quicker. Don't know how much there's to cover here. The first thing to note will be elemental resistance. Okay, so the first thing we have here, this is showing just the elemental resistance part of it, because each one of these paths have the same basic resistance. But you'll notice here that these fire charges, they're fine going down an earth conduit, but water will not go down an earth conduit. I mean, it will if you force it, but, it prefers not to. It likes water conduits. But fire does not like water conduits. Same thing. If you send fire down a water conduit, it will be attenuated, so it will actually lose some of these charges here. The number will go down if it gets sent down a water conduit. These water elements here are actually damaging the fire conduit, but it recovers fast enough that you don't notice it. But if you sent too much, it would degrade it to the point that they might fry. So you kind of have to be careful. Previously, I'd mentioned that water's fine going down a fire conduit, which it is, but the conduit itself is not. So you'll want to consider when you're making your elements. But because of this, you kind of have a Maxwell's demon here, right? Because it sorts appropriately at each of the one of the conduits based on this elemental resistance. This one here, this is still fire, so you'll see that the fire and the water will go down this one just about the same. But if you were to say delete this, you'll start seeing them pretty much sorting themselves out. Some will go down the wrong conduit, but it's pretty rare. Essentially, the stronger conductor it is, the greater the effect. So like these here, they have a resistance of 0.1, so their conductivity is 10. So what that means is if you're a fire element here and you're picking this one or this one, well, this one is 10 times, the factor would be 10. Basically, it's going to be either the sigma, the conductivity, over the resistance, or 1 over sigma times the resistance based on whether or not they are aligned or anti-aligned. So for this one here, it's going to be seeing, 10 times 10.1, something like that, 10.2. So 1 over 100. And over here, it's going to be seeing essentially 10 over 10.3. So yeah, it's going to have a higher probability over here than over here. So that's why you'll end up getting them switching pretty well, pretty consistently between them. Now let's set up a different thing. So here we have a NOT gate, or just an inverting circuit, as it would otherwise be called. You can see here there's a pull-up resistor here, similar resistor over here, and I'd been using an inverting rune because my system as it existed before simply could not do what is needed for an actual NOT gate, which is this inverting circuit here. When you have your pull-up resistor and you split off here from your switch that shorts to ground, that's an inverting circuit. So yeah, you can see here because power is going to this transistor, power is being shunted here to the ground. And you'll get very little is going to go over here to this emitter. But if you switch it off here, pretty much all your stuff's going to be shunted over here to this emitter. Now there's not a lot of power going to it because it's, this is a 1 kilo ohm resistor, so the overall current's pretty low. The current is actually higher than it should be, and the voltage is a lot lower, and I'm not certain why. I had to find that one out still. I think that's a bug to fix, but yeah. You see you get a lot more power through this way. 8 amps coming down this way. Again, I'm not sure that's accurate, but it is working conceptually, but I do think the numbers still need to be tweaked a bit to make sure they're accurate. The resistors over here, rather than having a quadrillion different types of resistors, like anybody who's worked with circuits is probably well aware, I have a much more simpler. These resistors are variable. Ooh, I can't. Yeah, that doesn't look very good there. Cancel. Cancel. Well, I'll have to do something about that also. I'll go with this one because it's easier to see what it looks like. Yeah. So the main thing here, this is where you're able to set your resistance. You can set it up to 1,000, and then you can set these with milliohms, kilo ohms, mega ohms. It's about as high as it goes for ohms. This one is set to 100 ohms. This one over here is 1 kilo ohm. So I am probably going to be having a puzzle for the NOT gate instead of having a the inverter rune, and we'll do something about the inverter rune. You can see a couple of them, little stray ones that do go over to that emitter. It is always just fun to watch these. I rather like it. That's why I'm no matter what sort of problems happen, no matter what sort of issues come about from the fact that electricity doesn't actually move like that, and it messes with things, I am never getting rid of these numbers. I love those things. They're just so much fun to watch. They are the best thing about this. But yeah, that is the inverter there. So another thing to do with resistors, where there will be variance on resistors, there probably will be more than one type of resistor because you're going to have to handle different amounts of wattage and amps. Like this thing here, it's only got 5 watts of power dissipation. If you keep putting more than 5 watts, you're going to burn it out. Same thing for this fuse up here. It's got 5 watts. Pretty much everything on here has about 5 watts of power dissipation. And if you put more through it, it'll fry, except for the runes, because runes do not fry. So the fuse is there because if I can actually probably just show you what will happen here. So let's take this resistor. It's a 1 kilo ohm resistor. Let's drop it down to 1 ohm and let power go. It's weird those guys kept going after this thing shut off, but anyhow, yeah, you can see this fuse has blown. And so now there is no longer any current running through here. There shouldn't be any voltage, so that's another bug that will need to be resolved. They wouldn't have kept going if that thing had properly responded as if it were an open circuit, which is what it is right now. But a nice thing about these is you can delete them and you can just put them right back in. And let's put you back to 1 kilo ohm so we don't blow the fuse again and let things go. Yeah, the fuses are made so that they have one point of health. That's all they have. If they lose that, they fry, which is kind of what you want. You want it frying and not anything down here, and certainly not this. If this fries, like if this was a conduit instead of a fuse, if it fried, it would be considered a short to ground as far as this is concerned. And this crystal will keep shunting power straight into it, and it will overheat and it'll explode. So these things are really nice. They're good for safety. They're good for when you're working on a circuit because you don't want to have to remake it every time you blow up your shop. You know, just those useful things. I don't know if I'm going to incorporate the safety aspect of it into the game, like, you know, dissatisfied customers because your crappy magic item blew up their house. But yeah. So what we will be having though, as far as the resistors go, it will be resistors that have higher power ratings. So you can use them in more high power circumstances, and similar for the fuses where they will have higher power ratings so that they won't fry if you're sending too much power, because you do have to send a good amount of power often. Like you can see this thing's set up for 20 watts. If I was trying to send 20 watts through here, I'm going to fry that because they can't handle 20 watts. They can handle 5 watts. Although I don't know that matters to them as much, but it would a bit, because this one has like a 10 amp resistance. If this is 10 amps over here, I don't think you'd get 20 watts, but you know, it's going to be dissipating heat as well. So yeah, primarily you want this getting a lot less. One thing you can do, of course, you can put them in parallel, or you can split them up in series. Things like that, I believe, still work. I haven't tested it yet. But yeah, just little things about resistance. Resistance primarily, like, if you're not familiar, resistance. So the main thing to note with resistance is going to impact how much power is going to be dissipated by that element. All these things, they have resistance. Like these are wyvern blood, so they don't have very much resistance. It's actually, I need to do something about the display on this resistance so I can show micro ohms or pico ohms or whatever that is, because it is a very small number. I think the conductivity is like 4 million, whatever S is, I don't remember. But sigma is that thing for it, but it's about 4 million. So it's 1 over 4 million is your resistance. So it's a very small resistance, and that's about that's not the resistance, that's the resistivity, sorry. It's about conductivity and resistivity are inverse of each other. But it is that is the conductivity. It's about 4 million. The cross-sectional area is 0.5 inches by 0.1 inches, and it's a 1 inch long thing. So essentially, if this were a piece of copper with those dimensions, this wyvern blood would have the same resistance as that piece of wire. So that's why I say it's basically negligible as far as these go. But the other ones, like the salamander blood, they have a 0.1 resistance. So their resistivity is like 0.05 or 005, something like that. So it has a significant resistance. And what it means is that when these charges here, when they go to try to move through one of these conduits, when they're moving through, they are dissipating energy. That is what your resistance does. Is it takes some of the energy that from the current and it puts it out as heat. Now, how it dissipates it is complicated when in real life, and I didn't simulate all that. Instead, I just wrapped it up in a nice little number I call power dissipation. So I say that, you know, they all have a power dissipation of 5 watts. That means they can somehow, some way, get rid of about 5 watts of continuous power without heating up. Maybe they put it through their entire, area, whatever. But if you go putting in more than that, you're going to start getting accumulation. Kind of like in a wire. If you put too much amps through a wire, you can put a good amount through. It's not going to heat up much, or possibly at all. It'll dissipate its heat either into the air or through its links, or however it does it, But when you go above a certain amount of current, that's usually called the ampacity of the wire. When you go above that much current, you start actually heating it up. And what's actually happening is it's the power dissipation. It's just that because the resistance of the wire is fixed, the only thing you really have to care about is the current. Because power dissipation is current squared times resistance. So the resistance of the wire, you already have that set. So you basically just take the square root of to get the current thing, you just take the square root of that property, I think. So you just need to know, if you know how many watts it can manage to dissipate, you can just take the wattage, and you can use the square root with the power formula there that I mentioned before. I squared times R, take the square root of that, and you'll get you'll get your eye. I think it's something like that. So, you know, I've done that, and actually, these things here, they will show you their max current. Like, despite the fact that like the resistance is very low, it does have a maximum current. Like 607 amps is the max current for this section of wire. So it can take quite a bit. Is that accurate? I'm not certain. But like, would that be accurate for a wire of that size? Let me check something here. Okay, so the way that I calculate, I take that power dissipation in watts that I mentioned before, and I divide that by the resistance of the conduit itself, and I take the square root of that result, and that is what is giving you that ampacity over there. Pause this. That's what's giving this max current there, that 607 amps. Now, like I said, is that true for a wire of this size? I wouldn't be too surprised. I mean, that is a decently sized wire, all things considered. I don't know what gauge that would be. Should probably look it up. I'll look it up. Let's see. Actually, I'm not going to look it up. Now that I think about it, there's too many things that are off about it. Like I put in my, let's see, I put in the power dissipation as a fixed thing, but that's not really a thing. So I wouldn't draw too many comparisons there. In terms of game, though, if you put more than 607 amps through one of these wires, they will fry. But that's why you have things like this fuse, which will blow before any of these do. It's got about the same power dissipation, but a much higher resistance. It's a 0.2 ohm resistor. Aside from being, a fuse, it's also a 0.2 ohm resistor. So between these, we have a 1 kilo ohm resistor, a 0.2 ohm resistor. So it's 1,000.2 ohms is what is in this series here, and the negligible amounts from these. But yeah, that is primarily what resistance is in a wire, and it will contribute to your power loss. It's also useful when you're talking about splitting off voltages. Yeah, I think I mentioned previously about voltage splitting, where we have our, let's see, this one isn't getting a voltage split because there isn't a resistor over here, so I think we're getting pretty much the same voltage, but there is a change in voltage. To see if there was a wire here, you'd probably see the change in voltage from before and after the resistor, but most of these resistors are right next to fuses, so I can't show that off very well. I do intend to have a tooltip on these to give information about them. This one's supposed to have a tooltip, but I don't have it in here. That tells you the power output. But yeah, I'm also going to have one here for the transistor rune to tell you would it be VB, VC, and VE, your 3 voltages, as well as IBC or IBE, IBC, ICE. Those sorts of things give you useful information about what's going through the transistor. Runes don't blow, but I wouldn't necessarily be opposed to having them influence neighboring things and make them more likely to blow. Like a transistor could be causing a buildup of the wires that are connected to it. So the transistor itself won't blow, but it might make things around it more likely to. And there's probably going to be like somebody who thinks, hey, this is basically a wire. What if I just wired nothing but runes together and get rid of the conduits altogether? Which you could probably do. The resistance on one of these is a lot higher than one of these, so you'll lose a lot of power from doing it. But there are things that'll modify the ability of a rune to conduct for ones that conduct, like these ones do. But you won't profit much from it, because the time that it takes to make an item with is based on what you actually do here. So each one of these things, they do take time to craft. When you go actually, like this is solving, this is research, right? You're learning how to make these to unlock the recipe, and you can revisit it. You can work the recipe, bring down costs and components and things like that. Each one of these runes, they take about 5 seconds. Same for the crystals. Conduits take like 0.6 seconds or less than that. So when you actually go to make one of these, if you made one out of nothing but these, they would take significantly longer to craft the item than if you'd made them out of the wyvern blood. But you would benefit to some extent because they are free and they are indestructible. So, you know, I'll leave that up to the player to play how they like. But yeah. So I modified that one a little bit. So here you'll see this is a NAND gate. Similar thing, just like how we had that inverter, all we've done is added an additional transistor right here. And so when this is off, it's going over there. Power goes to this output. Doesn't shunt to ground, but, and similarly, if only one of them is on, again, that probably shouldn't have happened there, but we'll check on it. But if only one of them's on, not much of a problem. Actually, that one moving was probably fine because power does run that way. If I turn both of them on, now we've created a short to ground, which is a preferential path over this path here. So all the charges want to go this way. And so if both of these are on, nothing comes out of here. But if only one of them is on, things go out here. That is a NAND gate. NOR gates will work on a similar sort of principle, and that is why the inverting circuit is such a useful thing to have. Because the difference between, like, if this was an AND gate, instead of being up here like this, it would be down here, and the resistor would be a pulled down resistor down here instead of up here. Yeah, that is a NAND gate. That is how a NAND gate works. Let's see. We should also probably talk a little bit about these numbers now that I think about it. Because these are not things that exist in the real world. Obviously, these are magical numbers. And so, what the circuit here is modifying is, in many ways, the real world current that you would expect. And what these are, they're kind of like charges that ride that current. So, and they contribute to the overall power that comes out for any sort of magical things. These are the things which actually deliver the power to those things. So what you're modifying here, if you think about it like a river, you're modifying the flow of the river. And these are like little logs moving along the river. And they're the things that are doing your work. In the electrical circuits, like electronics and things like that, you don't actually care about the power. And there's a good chance that those puzzles, you won't even see the numbers because they're not important. All you're really doing in those is modifying your voltage, usually just the voltage, not even the current that necessarily matters as much. It's just the voltage that you're trying to modify in those sort of things. So I may or may not show the numbers in those cases. The main thing is going to be that the change in the voltage that'll happen for those. But there are more trees than just the electronics tree, and other trees will need these numbers, so they will be important. And I'm doing what I can to make sure that the animation doesn't impact negatively the availability of power. That's why these things will actually hold on to a number often before, when one of them gets to it, it'll hold on to it till the next one shows up. You can see that if I turn this off. I'm not sure if you're seeing it. I'm not even certain it's doing it, but it should hold on to it so that it doesn't fluctuate up and down between each pulse, because I don't want the animation to necessarily be limiting the actual power availability. but I'll need to work with that still to make sure that it is not sticking around more than it should, not staying less than it should. But it has a good, right, sweet amount of sticking around. And yeah, I've done a change quite a bit on how this thing does its power dissipation as well. Previously, when one of these numbers got to something that consumed it, it moved backwards through the chain and then distributed power appropriately for all of them. Now it actually does it as they move, which is, I think, more accurate. And it helps too because the fuse is up here, so you want this to blow before this blows. That's kind of its purpose. That is its one job. It's one job. Blow when too much power goes through you. So that is an important thing for that element. Something hypnotizing about these numbers. I just love watching them move. Something I imagine some of you will probably notice here is that numbers are coming out here, going into the base of this transistor, and then disappearing. You may be wondering where they go. Essentially, they go to ground, but not this ground. They've got their own sort of ground. I may do something with that in the future, because ordinarily in an actual transistor, what would happen is power when it comes through here, it goes from the base to the emitter and then continues along. This is an NPN, by the way, if anybody's wondering. These are modeled off of a bipolar junction NPN. I don't have anything for PNP. Hopefully that won't be a problem, but if it does become a problem, I'll probably find something I can do to either make this be able to be switched between PNP and NPN, because I do like that idea a lot better, similar to what I do here where you're able to double click on a resistor and bring up something to edit it. It'll probably be something like this where you could double click on one of these to change it from PNP to NPN, and then I might reuse my inverter room to swap this around so that it indicates that it is different. Instead of being that, it'd be the inverted thorn rune, or I might flip it upside down or something like that. You know, something so you look at it at a site and you're like, oh yeah, that's an NPN versus a PNP. You know, and these are NPN. So, but I don't want charges coming along here to contaminate this line. I feel like that would probably cause some problems. So instead of that, I have, like a lot of runes, they have their own built-in ground. This has its own built-in ground. This has its own built-in ground. It essentially consumes the charges. It's fine. Voltage does still move along there. You can kind of see it right there doing that. If I were to bring this up, yeah, you'd see there's about 815 millivolts on this, which is the same as you have over here, and that's because voltage does travel along here, and so would current. The current does go, but essentially the magical charges there, they don't. They go to ground, and there is a 10 ohm resistor across the BE connection there. So that does contribute a bit here. Now, one thing I'm seeing that I don't like particularly with this, like I said, I think it's a bug, is how much the current increases here. There is a current gain that happens, but this is I don't think the current here should ever be higher than the current here. And we're seeing, you know, a significant, like 100-fold gain. That shouldn't be happening. So I'll have to look into that to find out what's happening. But yeah, you can see what's going on here. There is, like I said, there are the resistors. There'll probably be different types of resistors that give you different sorts of wattage available, power dissipation. Like these are 5 watts. They're, you know, more than enough for electronic stuff, because really you're going to be using pretty high resistors when you're working with electronics. So you're generally not working with a whole lot of amps. Like this shouldn't have this many amps going to ground. That shouldn't be happening. So we'll find out what's going on there, but you would probably be more like this, where you have this 8.9 milliamps going to ground. Same sort of thing, you know, because you have that pulled up resistor there. So you might have just seen the screen go like move quickly there. I moved it down a little bit on my OBS. Yeah, I don't know a lot about video editing, so this is all new to me. I got this OBS here that I use for recording the stuff, and I got DaVinci Resolve that I use for editing, and I'm not very good at either of them. But yeah, we'll have multiple types of resistors for if you're dealing with high power things like the immovable rod. That is a very high power item right there. Like you're talking 8,000 pounds. You're talking an awful lot of energy that you have to deal with. You got to extract it, destroy it, maybe transmute it and emit it, whatever you're doing with it. That's up to you. I'll leave that up as an exercise to the person solving it. As long as it achieves the goal that it has, which is to, you know, not move when you have at least 8,000 pounds, up to 8,000 pounds on it. If it moves after 8,000 pounds, fine. But if it moves, honestly though, but if it does move, it's probably going to be because you fried a circuit. That's usually the case. You could probably make a way that it shuts off automatically if you put more than 8,000, but I don't think I'm going to make that a requirement for the puzzle. It is how the magic item in D&D works, but yeah. I'll have to go back and revisit the movable rod to make sure that it works fine with this existing, because as I've made changes to power dissipation and conduits and things like that, the things are likely to break, and I still gotta, I think the next video that I'll be covering will probably be capacitors, because I think that's going to be one of the big ones that I'm going to have to go revisit. Now with this new voltage system in place, I can make the capacitors actually work like RC circuits, like an RC circuit should, and I just think RC circuits are amazing. So I'm all for that. I have some ideas for how I'm going to be handling those to make them a bit more interesting and more fun. Right now they're nice. I do like them. I do like the capacitors because they smooth out your circuit, and it's always nice to have something to smooth out your circuit, you know. They take especially these magical charges here, because you can see how these low quality crystals here, they put out, you know, a range of different numbers. But maybe you want a specific number, because you want to really keep that consistency with your power. You don't want these rather, honestly, somewhat extreme fluctuations. I mean, a difference between a 5 and a 3, you know, is quite a bit. Especially because this is a multiplier on your power formula, so you're getting pretty good swings there. And when you're dealing with something like with the metal detector, where you need to make sure that your power is even across both ends if there's no metal nearby, so that they'll cancel each other out. But if, you know, that's closer to one end or the other, then that side should have more power than the other side, and so it should end up coming out as a result. And that comes down to these transistors. But also, if you're using these cheap ones here, you need a capacitor, because you need to be able to make that flow consistent. Whether the realistic capacitors would be able to do that is another question, but the capacitors will have a fixed output charge for magic units. That is an important part of how they function, so I like to make sure that is the case. The comparator rune, I think, mostly just goes on the magic number when it's deciding whether to create or destroy them. The comparator rune will probably also have to get some rework with this new electrical system, but I do think it'll actually make the electrical system it'll be a lot easier with the new electrical system, because it could almost probably work as, did I say comparator before? I just said comparator. I meant to say not comparator. combine rune. But yeah, the combine rune could probably almost work as a comparator with this new electrical system. Just because it'll be able to, check which of the branches that are coming into it have more voltage than the other, just by automatically, and it can output the appropriate thing for that. But I don't know. That's not exactly how a comparator works. This comparator has an input voltage as well that it uses into its own output, and yeah, we'll consider some other time whether or not I want to have the combine rune function in the same way as a comparator or not. But the combine rune can probably work out the output based on the elemental resistance, and then actually be able to modulate the voltage based on the type of element on each of the lines. So no, it wouldn't be able to do that because it won't know. It only knows when charges show up, so it still has to be on the charges. But so I'd probably have to like average out the voltage for the output or something like that. However, the case I decide to do that, I'll be working on that sometime in the future. Because with these changes, a lot of things have to change downstream to accommodate the new way these are functioning. But yeah, that covers a lot of the stuff related to resistance here, voltage. Our inverter rune is going away, and the NOT gate, it'll probably be a component similar to the existing gates that I have, my OR gates, AND gates, XOR gates, etc. Those are components that after you solve the puzzle, you're able to use them. They'll be keeping track of what scale you made them at, because you'll need to give some consideration of the scale that you made them at for the scale that you're using them at, because you can only really go one scale above what you're using them at, what you made them at. Because I can't really have you using a component that takes up like a quarter of a square. I wouldn't know how to do that. I think there'd be a lot that I'd have to go into to allow you to do something like that, and I don't know that the two should be worth the squeeze. But I would like to tell more about the difference between a pull up resistor and a pull down resistor. I would like to, but I don't think I understand them well enough to do it. I do know that the pull down resistor, I think the purpose has to do with, like, if this over here, if it was down here, and the pull down resistor was over here, for instance. I can't tell you what difference it makes from it being over here. It has something to do with getting the voltage down below a certain thing for like a logical high versus logical low, high versus low voltage. But I couldn't tell you why, or if indeed my system accounts for that. I'm pretty sure it does. I think I'm calculating all my resistances correctly, so even if I don't understand how it works, I do think it will still work. But I do know that generally you put the pull-up resistor goes before the branch out to the output, your logical output. A pull-down resistor goes after the break and between ground. And when I'd heard it explained, it had something to do with floating voltages or something like that. I think it was just to keep it consistent. But I don't know why it's different here versus here. It's probably something to do with the branch, I guess. But yeah, presumably if everything is working correctly with the resistors, that will make a difference when they're solving the puzzle. And of course, I'll need to make sure that I have a few components here that are just for me. That I have them here because I need to put them in puzzles in order to be available. Signal source, power source, and signal output. I don't know if I'll have those anywhere else. I do intend to have something for holes, pass-through points, because some of the puzzles are forward and backward, so it allows you to pass voltage, through it to the other side. But I haven't made those. But yeah, the signal source, signal output. Right now, my signal output is serving as my ground. Anything that consumes charges can work as a ground. The signal output has the thing. For why it's using it is because it doesn't have the built-in resistor that the runes do. So it's not going to be functioning, like that pull-down resistor I mentioned before. But in the case of an AND gate, like this is an AND gate, but if I was making an AND gate, I could actually just replace this here with a emitter rune. It'd have that 10 ohms resistor to ground, so it's already functioning as a pull-down resistor, presumably. Presumably. I'm not actually certain on that one. But anyhow, as I was saying here, our signal source and our signal output, one of the things we'll want to do here will be, because those act like our logical voltages, we need to make sure that the signal output really is only going to accept a low if it is below a certain amount, and it's going to be high if it is above a certain amount, above that amount. So I think that's generally how those things work. They have a cutoff point for their voltage, and below that is low, above that is high. And as long as you can get there, you'll be fine. Same for the signal source here, where it'll pretty much just be putting out at either a low or a high for its values. Power source. My power source here is 9 volts, but I need to bring that down because when you're working with electronics, you're usually working in about the 3.6 volt range. So like here I have a crystal, but I'd have a power source instead, and it'd be 3.6 volts. I have a handy little thing that I use. I don't remember if I had shown it before, but I use this for just checking to make sure that my stuff is working as it reasonably should. And this is called Circuit.js. So I actually have that inverting circuit that I showed before. You can kind of see it here. It's not exactly the same because this one has a little LED on it, which has some resistance, I imagine. It's not telling me what it is, but it shows a voltage drop. And voltage drop means resistance, so I could probably calculate it if I were so inclined. I am not. But yeah, it's got this 10 amp resistor. That is that resistor to ground that the emitter rune has. The 1 kilo ohm, 100 ohm here, etc. This is an inverting circuit in Circuit.js, and yeah, this one over here, this is our NAND. It's plugged in. Let's plug it in. So this is what I was talking about here with the logical high, logical low. That's what these ones use. They use high and low, and this one could have an output over here to show it. But yeah, you can see how this works as a NAND gate. I don't know what I was doing over there. This is an XOR gate. There's a lot of power things on here that need to be plugged in before it'll work. So let's plug these in. It's probably not a very good XOR gate. This is one I think I made. So don't expect a lot. But yeah, when one of them is high, that one's high. If both are high, that one's low. This one has a massive pull-down resistor, 300 giga ohms. Why? Because I made it, and I'm not very good at this. Not much better of a reason for that. But it needed it in order to get this voltage down to the logical low. When this is like that, if this wasn't there, this would actually still be high. Like it's teetering there. It's 1.375 volts, which I think is teetering on what it considers a logical low. Of course, unplug both of them now. It's still 1.35. Yeah, I got a little chart down here. I'm tracking, I think, this thing. It's a nice little application. I like it. I use it a lot to, like I said, to check the circuits that I'm making to make sure that the numbers are at least like close to each other. Maybe they're not accurate. The only reason I disconnect this, by the way, is so that it doesn't waste a bunch of time doing stuff. So it's not calculating things. Turn it all off. Let's see. Similar over here. Go ahead. Unplug these guys. So this one over here, and you can see from this, like this is showing that my current through this wire should be about 7 milliamps. If this is connected, current through here is 91 milliamps. Up here, oh, actually that is quite a gain, isn't it? There's a gain in current from here to here. This is 8 milliamps, and down here it's 91 milliamps. So there is a significant gain between these two. Something to consider when I'm figuring out what's going on there, but probably not something you're interested in, so we'll continue on with what we were doing. But yeah, that's a nice little tool if you ever want to look at it, if you're interested. Lets you build circuits, test it. It is not something that I created, obviously, but it is something that I like and helps me in my development here. But yeah, I think that covers most of the interesting stuff there related to resistance. I think the next one will probably be on capacitors, which means it'll be a long one, I'm sure, because there's a lot to talk about when you're talking about capacitors. One of the ideas I'm having for that though is I'm going to have instead I'm thinking of having it show the charge on each of the plates and maybe having the charges build up on two sides of the capacitor, so you actually kind of see it, because that's what happens on a capacitor. If you're not familiar, it's essentially the electrons, they'll collect on one side of a plate and they'll push electrons off the other side of the plate, and that allows them to go, and then as more electrons gather on one side of the plate, the other plate gets more and more depleted, and the current slows down. Once the voltage of the capacitor is equal to the voltage of the input source, then current stops completely, and that's basically at the point that it can't push any more off the other side of the plate, and it can't gain anymore. So yeah, that's how your capacitors work. And then of course when you disconnect, now the voltage is able to continue on the other way. So it'll discharge back the way you came, and it functions a little bit like a battery, which is, I'm almost certain, going to wreak havoc on my circuits. So I'm going to have to consider, like, there's one of the facts, of course, is that there's all of the conduits are diodes, so you're dealing with capacitors connected to diodes, not capacitors connected to wires, which is how a lot of people tend to use capacitors, because they go back out the way they came, and they're not able to go back out the way they came, so they got to go back out through a different way. But beyond that, I can manage the charge-discharge by managing the voltage across the thing, so it'll be able to handle the charge-discharge, I think, just fine. And that'll be the main thing to deal there. And like I said, there'll be a lot to get into when we're actually talking about the capacitors, because you're going to be charge curves, discharge curves, e to the power of RC. It's a mess. But hopefully the mess is just for me. Like, I'm the one, I make this, and I see what I want is for everybody who's using it. You're using this, you're not seeing e to the RC, etc., etc. You're seeing numbers moving through a conduit. You're seeing bars go up on the little graphical element that comes up. You're seeing the overall chart. You're seeing the effect, and you're hopefully seeing it in a way that makes sense and is intuitive, so that if you're not an engineer, you're not like that, you can still have fun. That's what I want. I want you to have fun, but I also want it to be accurate. So I am going to make sure that I get these things to get that nice point between accuracy and fun. And yeah, hopefully I'm hitting it. It's fun for me. I like these things. I really like what. I'm just gonna turn on those numbers just because I love watching them move for those things. They're just so much fun. They are hypnotic watching them move along the circuit. That's one of those things I love about it. And yeah, and you'll be able to make cool stuff, sell it. I'm hoping people enjoy it. That's all I can say. Hopefully people enjoy playing it as much as I've been enjoying making it. And I think I'll leave it on that. So, till next time, we'll be talking about capacitors. There'll be a lot to it. See ya.